Okay, fine. Myself, Dr. Abarna Thagapan, Assistant Professor, Department of Physics, Basilius College. Today, I am going to discuss about orbital magnetism and the normal zeeman effect. The orbital magnetization is nothing but it is the magnetization induced by the charged particles, usually electrons in solids. And we know that an electron orbiting the nucleus of an atom should give rise to the magnetic effect, much like those arising from an electric current circulating in a wire loop. In particular, the motion of the charge generates a magnetic field within the atom, and the atom as a whole is subject to force and torque when it is placed in the external magnetic field. These magnetic interactions can be described in terms of a single property of the atom, that is the magnetic dipole moment. Okay. To calculate the magnetic moment of an orbiting charge, that is the moment mu of the loop, mu is equal to I times A, where A is the current, where I is the current and A is the area bounded by the loop. The direction of this moment is perpendicular to the plane of the loop, and its sense is given by right-handed rule, that is shown in figure figure A. This characterization of a current loop as a magnetic dipole implies that its magnetic behavior is similar to that of a bar magnet, with its north-south axis directed along mu. That is in figure B. For a circulating charge Q, the current is simply Q by T, that we know, where T is the orbital period. Furthermore, A by T is L by M, where L is the angular momentum and 2m, that is 2 times the particle mass. So we can divide A by T, it is the area swept out per unit time, and is equal the magnitude of angular momentum of the orbiting charge divided by twice the particle mass m. This relation easily verified for circular orbits, where L equal to mvr, v is equal to 2 pi r divided by t, and a is equal to pi r square. So that L equal to m into 2 pi r divided by t into r equal to 2m pi r square divided by t, that is equal to 2m a by t. The same result holds good for the orbital motion. So mu is equal to q by 2m times L for the magnetic moment of an orbiting charge Q. That is, mu is equal to magnetic moment of an orbiting charge, where the Q by 2m is known as gyromagnetic ratio. For electrons, Q is equal to minus E, so the direction of mu is opposite to the direction of L. On the atomic scale, the elemental unit of angular momentum, that is L, is h cut. It follows that the natural unit for atomic moment is the quantity E h cut by 2me. That is called Bohr magneton. That is denoted by the symbol mu b. Again, we noted that the unit of the Bohr magneton is Joule per Tesla. that is around 9.27 10 raised to minus 24 joule per Tesla. Because mu is proportional to L, the orbital magnetic moment is subjected to space quantization. In particular, the Z component of the Z component of the orbital magnetic moment is fixed by the value of the quantum number ml. We can write mu Z equal to minus E by 2me Lz, that is equal to minus E h cut by 2me ml, that is again equal to minus mu b ml. This the interaction of an atom with the applied magnetic field depends on the size and orientation of the atom's magnetic moment. Suppose an external magnetic field B is applied along the z-axis of an atom. According to classical electromagnetism, this atom experiences a torque, that is tau equal to mu cross B. That is the magnetic moment presses in a magnetic field. And that tends to align its moment, that is the torque tends to align its moment with the applied field. Instead of aligning itself with B, however, the moment actually presses around the field direction, that is presses around the field direction. This unexpected precision arises because mu is proportional to angular momentum L. That is, mu is proportional to angular momentum L. And the figure on the left side shows the orientation in the space and Z components of the orbital magnetic moment for the case of L equal to 2. Therefore, the multiplicity 2L plus 1, that is equal to 5, that shows the different orientations. And this figure on the right hand side, from this figure we can see that in a time dt, the precision angle increases by d5, where L sin theta dot d phi equal to dl. By using the above equations, we can combine dl equal to tau times dt, that is equal to q divided by 2me lb sin theta d theta. And for the electrons, we take q equal to minus e, that we know, and the frequency of precision, Lamar frequency, that is omega L, sorry, okay, something happened. Wait, be patient. Okay, fine. That is omega L equal to d phi by dvt, that is equal to 1 by L sin theta dl divided by dt, that is equal to E by 2me b. And we have the doubt, what is the use of this Lamar frequency? That is, it is the important parameter that introduces the quantum of energy, that is h cut omega L, that is associated with this Lamar frequency. And this energy is related to the work required to reorient the atomic moment against the torque of the applied field. Okay. Now the work of the torque to produce the angular displacement d theta is dw dw is equal to tau d theta, and so dw is equal to minus mu b sin theta d theta, again equal to d of, we can write d of mu b cos theta, that is differential of mu dot b, and we can write this work done. Just a minute. Okay, this work done is taught as orientational potential energy of the dipole in the field. So writing dw is equal to minus du. This du is identified as magnetic potential energy. That is, the energy of a magnetic moment depends on its orientation in a magnetic field. So we can write u equal to minus E by 2 me L dot B. EB by 2 me L is H cut omega L M L. So we can write the total energy of the electron is the sum of the magnetic energy U plus whatever the energy it had in the absence of the applied field, say E0. That is E0 plus H cut omega ml. And also noted from this equation, this it has the value of ml. From this it is clear that this energy, that is the energy of a magnetic moment, that is quantized for m, that is depends on the orbit magnetic quantum number ml. So this must be quantized. And now we go to an example of the hydrogen atom in its first excited states, that is n equal to 2. N equal to 2 states. For n equal to for n equal to 2 states, L can have two values, 1 and 0. The magnetic field has no effect on the states for L equal to 0, since here ml equal to 0. But in the case L equal to 1, it splits into 3. That is ml equal to 1, 0 and minus 1. That is for L equal to 1, ml can have 3 values. That is, in other words, we can say our excited level is split into 3 in the presence of the magnetic field. Here our original transition, that is n equal to 1. For the hydrogen atom, we know that this transition is known as Lyman. And the central line appears as omega 0, the same frequency as it would without the magnetic fields. It is the same position, omega 0, the spectrum without magnetic field and the spectrum with the magnetic field. But in this, the most prominent thing is that there is the two frequencies on either side of the central frequency, that is omega 0 plus or minus omega L. Omega 0 plus omega L here, omega 0 minus omega L here. So we can say that there is splitting of spectral lines with the presence of the magnetic field. That is, one line is split into 3. That splitting, that is in the by the magnetic field, is known as normal zeeman effect. The name after its discoverer, Peter Zeeman. Okay, I think everyone's understood this. Okay, and now we go to more complex. The transition n equal to 3 to n equal to 1. Here the situation is more complex, but when we observe the zeeman spectrum, this is not complex. The reason is, I will tell you. Okay. Here the zeeman spectral lines and the underlying transitions that give rise to the for an electron excited to n equal to 3 states of the hydrogen. Because of the selection rule, that is the important, that is because of the selection rule, there is only permitted transitions. That is not that is denoted in blue color. That is there is the blue color is is the transitions that occur. Other transitions are prohibited due to the selection rules. That is, these selection rules express the conservation of the angular momentum. Okay. Here n equal to 3, there is ml can have the values L equal to 2, L equal to 1 and L equal to 0. ml can have the values as plus 2, 2, minus 2, plus 2, plus 1, 0, minus 1, minus 2. And n equal to 2, L equal to 1, ml can have the values plus 1, 0 and minus 1. Here the blue transitions in blue color are only the zeeman, that the only transitions are the behind the zeeman splitting. And finally, we can say that the splitting of the emission line into triplet of equally spaced lines. I repeat, splitting of an emission line into a triplet of equally spaced lines. That is the normal zeeman effect. But more commonly, the splitting into 4, 6 or even more unequally spaced lines are seen. That is anomalous zeeman effect. I will discuss about the anomalous zeeman effect in the coming section. Thank you for watching.